The relative velocity is the velocity of an object or observer B in the rest frame of another object or observer A. Classical mechanics. Equals in one dimension equals. We begin with relative motion in the classical, that all speeds are much less than the speed of light. This limit is associated with the Galilean transformation. The figure shows a man on top of a train, at the back edge. At 1 p.m. he begins to walk forward at a walking speed of 10 km per hour. The train is moving at 40 km per hour. A figure depicts the man and train at two different times, first, when the journey began, and also 1 hour later at 2 p.m. A figure suggests that the man is 50 km from the starting point after having traveled for 1 hour. This, by definition, is 50 km per hour, which suggests that the prescription for calculating relative velocity in this fashion is to add the two velocities. A figure displays clocks and rulers to remind the reader that while the logic behind this calculation seems flawless, it makes false assumptions about how clocks and rulers behave. To recognize that this classical model of relative motion violates special relativity, we generalize the example into an equation. Where is the velocity of the man relative to Earth? Is the velocity of the man relative to the train? Is the velocity of the train relative to Earth? Fully legitimate expressions for the velocity of A relative to B include the velocity of A with respect to B, and the velocity of A in the coordinate system where B is always at rest. The violation of special relativity occurs because this equation for relative velocity falsely predicts that different observers will measure different speeds when observing the motion of light. Equals in two dimensions equals. The figure shows two objects moving at constant velocity. The equations of motion are where the subscript I refers to the initial displacement. The difference between the two displacement vectors represents the location of B as seen from A. Hence, after making the substitutions, and we have. Though easy to learn, this notation is unfortunately a bit cumbersome for lengthy calculations. Equals Galilean transformation equals, to construct a theory of relative motion consistent with the theory of special relativity, we must adopt a different convention. Continuing to work in the Newtonian limit, we begin with a Galilean transformation in one dimension, where x is the position as seen by a reference frame that is moving at speed, v, in the unprimed reference frame. Taking the differential of the first of the two equations above, we have, and what may seem like the obvious statement that, we have. To recover the previous expressions for relative velocity, we assume that particle A is following the path defined by dx dt in the unprimed reference. Thus and refer to motion of A as seen by an observer in the unprimed and primed frame, respectively. Recall that V is the motion of a stationary object in the primed frame, as seen from the unprimed frame. Thus we have, and, where the latter form has the desired symmetry. Special relativity, as in classical mechanics, in special relativity the relative velocity is the velocity of an object or observer B in the rest frame of another object or observer A. However, unlike the case of classical mechanics, in special relativity, it is generally not the case that this peculiar lack of symmetry is related to Thomas precession and the fact that two successive Lorentz transformations rotate the coordinate system. This rotation has no effect on the magnitude of a vector, and hence relative speed is symmetrical. Equals parallel velocities equals, in the case where two objects are traveling in parallel directions, the relativistic formula for relative velocity is similar in form to the formula for addition of relativistic velocities. The relative speed is given by the formula. Equals perpendicular velocities equals, in the case where two objects are traveling in perpendicular directions, the relativistic relative velocity is given by the formula. Where the relative speed is given by the formula. Equals general case equals, the general formula for the relative velocity of an object or observer B in the rest frame of another object or observer A is given by the formula. Where the relative speed is given by the formula. See also, special relativity, composition of velocities, velocity addition formula, Wyckoversity special relativity. Notes. References. Alonso and Finn, Fundamental University Physics ISBN 0-201-56518-8, Greenwood, Donald T., Principles of Dynamics. Goodman and Warner, Dynamics. Beer and Johnston, Statics and Dynamics. McGraw-Hill Dictionary of Physics and Mathematics. Rinner, W., Essential Relativity. Kermier S., Mechanics, Engineering Mechanics, Statics, Dynamics. External links, Relative Motion at Hyperphysics, a Java applet illustrating relative velocity, by Andrew Duffy, Relata v. Mosca S. 3. Relative motion of two-train. 3. Videos on the portal Physcip. Sebesa copyright Gecker paragraph Sexa copyright Save relative tranquility of trout in creek. Video on the portal Physcip.